Okay, so let's look at the word problem. Two inputs, x1 and x2, single output z. x1 and x2 are never one simultaneously. x1 and x2 are never one simultaneously. Okay, when that combines with a requirement that they both cannot change simultaneously, it greatly reduces our state table. The output of z1 is to occur only during the input state x1, x2, after having recognized these. So looks like a more kind of a problem. All right, let's call this state A. That means it's recognized this. B and G, which is this last 0, 1 again, where the output's a 1. The rest of the time the output here is a 0. So our present state and our next state for x1 and x2, 0, 0, 0, 1, 1, 0, 1, 1, and then our output z. All right, we have our states, A, B. Okay, at A we're stable, and we've received a 0, 1. Now here we cannot ever go here because that would be a 2-bit change. We can never go here because that can never happen. So you see how this all of a sudden gives us two don't cares. And our only option is to go to state B. To sit there and wait for state B. Now at state B, we wait for a 1, 0. That's state C. Now we can never go here from B because that would be a 2-bit change. Now from B, we could go to here, and we would want to go back to A and start over again. Now at C, we're going to slip down, go down here to C. That's the stable state C. We can never go to here because that's a 2-bit change. And if we get a 0, 0, that means we go down to state D. Now at D, if we get a 1, 0, we go to E. We can never go here. What happens if we go here at state D? We go to a 0, 1. Well, we'd have to go back to A, start over again, if we're going to be consistent here with B. Okay, stable state E. So you see how there's one stable state per row, right? Now we're at E. Can't go back to here. Can only go to here. That's to F. F, if we went to here, we'd have to go back to A. No, we would go to G. Yes. Down here to G. If we're here at F, can we get here? Yes. Where would we go? 1, 0. We're at F, and instead of receiving... let's leave that blank for the moment. Okay, we're here. We can never get to here. And we're going to have to start over again at B if we get a 0, 0. Because we've already got a 0, 1. So we have an output here, 0, everywhere except for at the bottom. So what do we do about this box right here? We're at F. We're waiting for the 0, 1, but we don't get it. So we've got to get our way back to the beginning. Well, in a sense, it is the beginning, because then we need to start waiting for a 0, 1. Whatever the wrong value is here, well, let's see, what could it be? It'd be a 1, 0. So let's go here to H, and let's just call H here wrong. And what are we going to do here at the stable H? Well, we're going to output a 0 because it didn't work. And what are we waiting for? We're waiting for a 0, 1 to get back to A. But we can never get there from H because that would be a 2-bit change. So what we have to do is go down here to I. So let's just call this state waiting. This is the waiting state. And at I, we're waiting for a 0, 1, which can get us back into the loop again here, get us back into A. And what happens if we get a 1, 0? Well, let's just stay down here, slip up to H, and just force ourselves to go around in a loop until we can get started again in the whole process. Now I've checked this with the next slide, and they agree, except for this whole output right here was mealy. Let's just stick with more. Okay, so now time for a bounce test. We're going to start off here at A. What we're going to do is bounce back to A, then back to B again, and see if we land at B. So we're going to bounce back to A, and we slip up here to A, and then back to B, and we end up here at B. So the variable that's changing here is x2, and we started off at B. This is the present state, present, and this is x2's value, 0 and 1. And then went to a stable B, and then went back to A in our bounce test. So we started off here going like this, successfully, and then we bounced. We went back here to A, slipped up here to A, and then bounced back to what was hopefully B again, and it was. We're going to do a bounce test on B. So here's what we want to have happen. We want B to go to C, and then we want to slip down here and stay there. The trouble is, if we bounce back to B, we're going to slip down here to D. And then when we go back to what should be C, we end up here at E. So this is a failure. So when we were looking at x1 as our input, B as the first state, we were starting off here at a stable B when x1 had a value of 0. And when x1 had a value of 1, we went to C. C turned out to be stable right here. Then we bounced back here to D, and D slipped down here to D. D moved to E when we bounced back, and so instead of ending up here, we ended up here. So this was the desired path, slipping down here to state C, and then this was the bounce path. We went back to what we hoped was B. It didn't end up at B, though. We ended up at stable D. And then when we bounced back, we ended up here at E. How is our circuit going to behave? How do we fix this? That's the question. So our first test passed, and our second test failed. We have 3 questions. Number 1, what causes this in the first place? Number 2, what are the known solutions? And number 3, will any of these solutions work for us? So this is an explanation of what causes these problems. We've taken those 2 examples and shrunk them down and showed that they're basically the same. We were going from A trying to get to B. Well, actually it was B going to A, I forget. And this was B going to C, whatever. The inputs here were slightly different. This was x1 and this was x2. We're trying to describe why this occurs. Why is it that when we change our inputs, we don't shift to this column immediately? The bad thing that happens is we slip down the column associated with the previous input's value before we move across. In synchronous networks, we always went from left to right and zigzagged around, right? And we've been assuming that we always move from the current input value to the next input value and jump from one column to the next. But why? We could just as easily go down this column and then across. And that's really all we're doing here when we end up here at C instead of the desired B, or where we end up at D instead of the desired B. So the reason why is symmetry. The reason why is an imbalance in the delays, a tipping point between going one direction or the other, going across versus going down first. The second question was, well, what can we do about it? The general answer is just plan on one of these 4. And if you don't like one of these 4, then do the bounce test and build your own. The third question is, well, can we find a solution? Basically, we want to do this to the problem that we're having. but we can't. There's not a solution for this problem right here. So for the moment, because we cannot visualize a solution, because there probably isn't one, let's go on and see if the problem shows up after doing everything else that we need to do for an asynchronous sequential network, and maybe try to solve it with some delays. So we really shouldn't have done the bounce test at the state table level. We should do it after the implicant table. Here you can see I've done an implicant table and found out that A and B are equal and H and I are equal. So I've collapsed them into B and collapsed them into H. So what we want to do is the bounce test over again. And let's just document what we're afraid is not going to work so we can test it. So we're worried about stable B going to C, stable C, but actually ending up at E. And then, let's see, if we start at C, go to D, bounce to E, bounce back to F. So we're worried about C, which should go to a stable D, instead going to a stable F. We're worried about E, which should go to a stable F, bouncing down here to a stable H and staying here at H. So we're worried about E should be going to a stable F, but ending up here at a stable H. And F, not worried about. G, not worried about. So these are the three that we're worried about. Bounce, test, failure. All right, let's go on to the next step. Let's do a transition table. So for X1 transitions, it's this first bit. B goes to C, C goes back to D, D goes to E, E goes to F, F goes to H. For our X2 transitions, D to B, F goes to G, G goes to B, and H goes to B. So we have 1, 2, 3, 4, 5, 6, 7. That is one short of 8. I'm going to go with 3 flip-flops so I can build a bit bigger transition table here. I want to spread things out a little bit, try to get a jump on the 1-bit races. So we're going to have a Y1, a Y2, a Y3, and a Y4. 0, 0, 0, 1, 1, 1, 1, 0. I just want 1-bit changes between these. So it looks like B's mentioned once here, but it's mentioned 3 times here. So I'm going to put B right here, D above it, G below it, H right here, and then F I'm going to put right here. F goes to G. All right, so I've covered all of those arrows right there. Now I want to cover B going to C, so I'll put C right here. Now C can go to D through this slip right there. D can go to E. If I put E right here, D can go up and then wrap around and come in here. So that's D to E. E to F, I can slip like this. And F can go to H right there. F can go to G right there. G can go to B. H can go to B. D can go to B. So I've got 3 slips. So B is going to be a 0, 1, 0, 1, 0, 1, 1, 1. All right. I redrawn the state assignment right here. I put in the 2 critical races or slips that we identified on the previous slide. I've substituted for B its binary value, and now we're ready to design these races, these slips. Our first one is between C and D. You can see right here we're at C, stable C, and if X1 changes back to a 0, we need to go to a stable D. But there's a 2-bit change between C and D. So we need to add a new state here, J, and it's going to have a value of 0, 0, 0, 0. So we're going to put a J right here. And we're going to have C go to J and then J go to D. So there's no stable state necessary here at J. J is just a race. The whole thing is just a race. We'll deal with the flickering coming up. The other one is between E and F. We're here at a stable E, and we need to go to F. So we need to go through another state, K, and K has a value of 1, 0, 1, 1. 1, 0, 1, 1 is K. So E is going to go through a 0 right here, down to this state, 0, 1, 0, 0, and then it's going to immediately slip back up to F. So what we want to do is understand ASN transition table races. We've been using the word slip also up here. We started off with a 1 right here. Stable state C was going to go down here to D. But that requires a 2-bit change. That 0 right here has to change to a 1, and that 1 right here has to change to a 0. Now, what are the possibilities? Well, given this requirement, we could go up here to B and then maybe down to D. But we're not. That's not going to happen. We're going to get stuck here at B because B's stable. So there's this possibility that given this command, going from C to D, we actually end up here at a stable B. The other possibility is that instead of going from here to here, we go to a 0, 0, 0 state. This before this J existed. Remember, this J was our solution. Because remember, this 0 could hang around. And this 1 could change to a 0. Because remember, it's got to go away. So that this 0 could hang around, that 1 could go away, and we could slip from here down to here. And this wasn't even defined. This was undefined. Remember, it was don't cares. So whenever we were building our Carnot maps, it could go somewhere else. Who knows? So this is the problem here with this column. So let's say we're right here and we're being told to go to here. There's a 2-bit change. Now only 1 bit can change at a time. So we could actually slip down to here and be stable. That was going up here to B. Or we could slip down to some unknown state here and maybe not even end up at the right spot. This was a critical race, was replaced by an uncritical race. And it's this one right here. This is what we replaced it with. So let's say we're right here at the stable spot, and we're told to go to a 1, 1. Well, we go to a 1, 1, but then we immediately slip back up to here. That's what we designed. You see, we're here. We're told to go to here. Now this is our ultimate goal. We go down to here and then slip back up to here. We did that twice. All right, we're done with the races. Let's revisit the flicker one more time. We're going to go from, let's see, here to here to here and back up. So that's a 0 to a 0, so this better be a 0, otherwise we're going to have a flicker. And the other one was here to here to here. Yeah, 0 to 0, so we got to have a 0, so there'll be no flicker. All right, we're done. We're ready to start building this circuit. Okay, so now we get to build the circuit. First step was to re-enter this excitation table into a spreadsheet. And you can see the excitation table. These are the stable states in green. The next thing I did is I turned it into a truth table. The truth table is 64 lines long because we have 6 inputs. We have Y, I'm counting Y4, Y3, Y2, Y1, and then we start X1, X2. These are the defined Next states, this is the current state. These just repeat here. And anything that's not mentioned over here is I don't care. The next step was to enter this truth table into Logisim and letting its Quinn-Mikulski generate these equations right here. So here's what the truth table looks like in Logisim. Scrolling down through its 64 rows. And then these are the expressions right here that you see right here. There's y4, y3, y2, and y1, and z. We can't use this circuit right away. We have to go through and look for overlapping implicants. So we've got to go back and look at the K-maps. So I started off with the most simple K-map, which was Z, which obviously just has one implicant. And then Y1 had these three implicants, the green, the blue, and the red. And they all overlapped. That was good. And then the Y2 had 2 implicants, just the green and the blue. And so I had to make the red to overlap the green and the blue. Just scrolling down a little bit more, we can see that Y3 has 1, 2, 3, 4 implicants. So we've got the green, we've got the purple, we've got the gold, we've got the yellow, and they all overlapped. And the same thing's true with Y4. They all overlapped. So this was the only thing that has to be added to the circuit. That's what I'm going to do next. Okay, I could move all these things down, and that would work. But if I've made any mistakes inside that truth table, I want to be able to rebuild this thing without having to repeat the work I'm going to do now over and over and over again until I get it right. So what I'm going to do is go to main, and I'm going to put this thing in here. Okay, I built a circuit, and I'm trying to get it to work. I have this start button right here, which injects itself into Y4 and adds a delay, but that's the least of my problems. So I'm clicking on this to get it out of the circuit, and now we are at 1, 1, 1, 1, stable at 0, 0. So we're in this column, stable right here. So if I change to 0, 1, we should change up here, and it's not. Okay, how about 1, 0? We should change to this. We do. We go to this stable state, which is H at a 1, 0. So we're right here. Now if I go to 0, 0, I should stay there. Yes, I stay there. Now if I go to 0, 1, I should go back up to B. Yes, I go back up to B. Now if I go to 0, 0, I should go to this one. Yes. Now if I want to go to this one, I'm going to click 1, 0. Oscillation apparent. I've been playing with this for a couple of hours now, trying to figure out where to add delays, and I can't figure it out. I've checked my work 3 times. There's nothing more I can do. So I would probably start over by splitting state B back into A, adding another state for a slip, and the same thing with F, adding 2 slip states and separating them out into 3 states, because those are the ones that are giving me trouble right now. So that would start at the state table. It would require new state assignments at the transition table. What you're going to see coming up in the combination lock is a month's worth of work on that, and very similar problems at the beginning and towards the end that were solved by splitting the states up like I just described.